Several.
Go ahead with one.
There's more for the sake of it. I'm wondering what like other people have questions about the homework.
Okay, so here's a question. Maybe whether other people have questions about the homework.
Yeah, like on a scale of 1 to 10, how comfortable they're all 11.
Just kidding.
Okay, you have a question.
Can you go over the state functionality that you posted recently, where you save the picture to a file name?
Yes. So the question was, what about saving that picture to a file name? So what you need to do in your test.rkt file is you need to add this line of code, these 2 lines of code, into your test.racket, and then when you run some tests, you're asked to do a certain number of tests to produce a single blue square, a white rectangle atop a red rectangle, a yellow rectangle next to a white rectangle, and so on. In those test cases, the way I want you to make them is that you call that Mondrian function, you capture the output, the first one is the picture, you save the picture to files that I told you what they call test1.png, and so on, using this function. And then that way, the grader will just run your thing and then just admire the pictures that you generated. Yes, you have a follow-on question?
Will you pass in for the file name, or pass in like file one or?
You pass in one of the following 5 strings: test1.png,
Okay.
test2.png, and so on.
All right.
Yes.
So you state how many arguments, or not arguments, but random numbers are supposed to be consumed by, well, I guess it's not random in this case.
Yeah.
For the tests, but
Yeah.
can you state how many should be consumed for the other ones as well?
Yes. So let's start this thing from scratch. Maybe someone can take a snapshot of this later. So let's say that we have a large rectangle like this. And so now we're calling Mondrian. This might be, what, 300 by 200? And then some list of numbers. So that means that the width is 300 the height is 200. So this thing is going to at some point call Mondrian helper. With 300, 200 rands. And there's really only one reason that we need the Mondrian helper, and that is that in the helper, this thing is W, and this thing is H, if that's how you name their parameters. So that the helper, when it does step 4, that it has both the size of the current rectangle, which may be a teensy tiny thing inside the big one, and the size of the big rectangle. So at some point in the recursive call, you're going to have the width of the big one here, and the height, and then you have a small one inside here. So that's the significance of the helper. If it wasn't for that, you wouldn't need a helper. Yes?
Does the helper have to be inside it? Or I made it a free function, and I passed in the original height each time.
Oh, I see. You could do that. You could make it a function outside, and then give the helper these 2 as extra parameters. I have no
I
opinion.
had trouble getting lead rec to be organized.
Well,
as
yeah,
groups.
so I used the LETREC thing, but that's a way to avoid the LETREC. Yes, sir.
About the tests, for the first 3 tests, do we print the random number list of size 100 and then do we pass that to the subsequent tests or do we?
No, you can generate your own random numbers each time. So in fact, for the other tests, they're not random, right?
Oh yeah, either
For the other tests, you just pass in a fixed set of numbers that produce
it's
the
a fixed
desired
list
effect.
that produces the output.
Yeah.
And then for our own monitoring
You
optimization.
can put in whatever you want. Yes. So there was someone who said, well, he wanted to have that list of numbers to be in increasing order because it increased the beauty of his creation. Or, to which I say, whatever. I didn't care about that. So,
One more thing, I run the batch command, and it'll print things and it'll save pictures, but also it has some I think it looks like an error message at the top.
yes, so that's a very astute observation. When you run this command down here, there will be an error message that appears from the line that says #lang slideshow. That's a slide. Just ignore it. So you can, if you don't like it, you can take that thing out, then the error message will go away, because I'm importing the slideshow module like that, but if you leave it inside, I don't care. Okay, so I wanted to go back to this thing here, and talk about in more detail what goes on here. So the very first time, we're going to be calling Mondrian helper with W and H being the same as width and height. Now, what Mondrian helper does is it's supposed to make a decision whether the current rectangle should be split, and that decision depends also on the size of the initial rectangle, which right now happens to be the same, because we're starting off with the same. So what is the very first thing that we need to do here to do this step? What is the absolute very first thing we need to do?
Size is big enough.
We need to find out, is the size big enough? Is it wide enough? Is it tall enough?
Here's another thing. So at each stage we need a random number, and then sometimes you can see only 1 or 2.
Yes.
But if the list is empty, what I just did is I'll return the empty list again, but I'll pop.
I mean, if the list of random numbers is empty?
Yeah, if it runs out, then I pretend I get 0.5 and.
Oh, I see. You can assume that the list of random numbers is long enough that it will not be empty.
Okay.
So, yes, so you can just die with an error if the list is empty. I made no provision in my code for that.
So, we always consume one random number, right? To see if it's,
Yes, so that's what I wanted to talk about. So we're coming into the recursion, we're having a rectangle, and now we need to decide, is it big enough, tall enough, wide enough? In order to determine that, we need a random number, right? Because there's a random number in this equation. So I added this important comment to clarify what you need to do. Is you first get a single random number that you consume, and then you use that single number R for big enough, tall enough, and wide enough for these 3 determinations. That means that this R and this R should be the same thing. So if we look at this list of random numbers here, it's, what it is. There's a bunch of random numbers. So now we're coming into step 5, and the very first thing we do is we consume a random number. That tells us, is it big enough, and so on. So Now let's see what now happens. In the very first case, W and width happen to be the same. So W over width and H over height are going to be 1. And is it going to split?
For which one?
In the very first recursion. So we're calling it width itself. We're having a rectangle of size 300 by 200. Now we're passing that to the Mondrian helper. Will it split it?
Wait, what is
Is
R?
it big enough?
We are not ours.
Oh, doesn't that depend on R?
I'm asking that question.
Good.
Either way, no, it should always.
So we know that this one is 1, this one is 1. Is 1 greater than 0.5 times R?
Yes.
Yes, right, because R is at most 1. So the first time, we know for sure it's going to split both ways. Now it says we need to set the split so that the split falls between 1/3 of the height and 2/3, and similarly with the width, 1/3 and 2/3. Somehow. So apparently we need to compute this. So we need to figure out, where exactly the split falls. What is the first thing we do?
Calculating the split. What is the
Yeah.
first thing we do?
Yeah.
So we have to normalize R.
Before normalizing R, what do you do?
You need to consume one more.
Exactly, you consume a random number.
So this is the only case where we consume 2. The rest,
Yes.
we just use the original one we already did.
No. Otherwise you consume 1.
Yeah, which we did before, so.
No, you take a new one. So take a new number for the horizontal split, take a new number for the vertical split. So in this case you consume 2. You would consume only 1 if it was only split horizontally. You would consume only 1 if it was only split vertically, and we'll come later to the case, what if it wasn't split at all? Okay, so this number here you're done with it for the tall y. You don't use it again for the split. You get a new number for the split,
Okay,
or in this case you get 2 numbers because you need a split in both directions.
so we're always consuming either 2 or 3 random numbers each call?
That's correct.
Okay, so I can see.
All right, so now you get a number between 0 and 1, but you now need to figure out how to get to this point here. So you know that the width of the whole thing is W, the width of the whole thing here is H, and so you need to somehow figure out how to get to over here. So you should normalize your random number that's between 0 and 1 so that it falls between 1/3 and 2/3. So I'll just call that scale. So this would be the random number, in this case the second one, because we already pulled 1. And you multiply that by H. Then that gives you something between 1/3 of H and 2/3 of H, and that is the length of the segment here, right? If I were to call this one H1. Here. Okay. And that comes, now we're done with processing the big rectangle.
We thought the random number list was already in 0 to 1.
Yes?
So, what do you mean by scale? scales?
Well, it's not between 1/3 and 2/3.
Okay.
Because if you didn't scale it, then you might get very thin slices on the top or on the left or the bottom or the right. And Stevenson thought that was undesirable.
But shouldn't we do something then like scale it to 0 and 1/3 and then add 1/3 to that?
How you do that scaling, I leave it to your knowledge of middle school algebra. I mean, you just take a number between 0 and 1, then you multiply it with a third and add whatever. Then there's some linear transformation then. Okay, moving on. So now we recursively do the same thing here with these 4 smaller rectangles. Notice one thing, that when you do that recursive call, you're calling it for the first of those 4 rectangles. What random number list are you going to give it?
Could you go over that again?
Yes. When you're making the first recursive call here, what random number list are you going to pass on to the first recursive call?
Same with
The rest of whatever you receive.
Yeah, the rest of these ones here, right? At each step, you've consumed 1, and so now you take off the first 3 because that's how many you consumed. And that's the list that you're passing on to the recursive call for the top left. Now you're moving on to the top right. You need to compute its height and width. Well, the height and width, the height is the same as the first one. The width is going to be, W minus the width of the first one. So now you know its height and width. What random numbers are you going to give for the second recursive call?
The remaining minus whatever you read from the first square.
How do you know what I'm making the first recursive call ready?
Very carefully.
It returns.
Yes. The first recursive call returns the unconsumed numbers. Whatever that first call returns, you pass on to the second. Whatever the second one returns, you pass on to the third. Whatever that one returns, you pass on to the fourth. And whatever that one returns, you pass as the result of your call to Mondrian helper. That is an unpleasant set of a bunch of lets or letrecs, whatever. And in the complicated case of where you have 4, you have to kind of do this passing along all this number of times. It's simpler for if you just have a horizontal or a vertical split. So now let's assume we are in a recursive call. We're saying this rectangle here has become teensy tiny, 40 by 40 or something. And now we're coming back into the recursive call with a very tiny rectangle. What is the first thing we do? Excellent. We get a random number. Again, to make the big, tall, wide enough question. And now that is going to come out to say, no, it's time. Don't split it. What's the next thing we do?
Consume a number.
We consume a number. And then what?
Pick a color.
And then we pick a color, right? So this is to color. So that's what we do. And so you can see that the process of consuming the random numbers is completely deterministic. So that way, when I give you a list of not very random numbers that I've carefully chosen to produce a particular effect, I should be seeing the exact same effect with every correct solution. And then when I print out the unconsumed numbers, I should get the exact same list back. And that is what I'm going to do. So that's the reason I made you split up your solution into two separate files, the Mondrian racket and the tests on racket, so that I can run it both with your tests and I can run your Mondrian with my tests. And what I will do is I will produce what I think should be a single blue square and a white rectangle and a yellow rectangle and splitting it 4. And each time I will see, are you consuming just the right number of random values and are you producing just that rectangle? So I will print out, just like you will print out 4 files, I'll call them like my test 1, my test 2, and so on. And the grader will admire this. So make sure that you try out this procedure. You copy and paste your things into these into Mondrian racket and tester racket. Run it on the command line just like you already did, and so that you know that you have the files just. Any other questions about this? Yes.
For example, when we're assuming we come across a rectangle that's big enough, where we split twice, should we be trying to like build the HC append like inside the helper function, or should we actually be like drawing it right then and there and then moving on to
Well, no, you're not drawing anything, right? You have to produce a bigger shape.
Okay.
Yes. So what you need to produce is an HC append or VC append or an HC append or a VC append or the other way around. And I don't care much either way because they look the same. You need to produce that composite shape. Your output is two things.
Essentially be one large like nested append space.
Yes, it is a super nested HC-VC append, yes. And only at the very end in your testing case will you take the final shape and then draw it out.
Was the order of the splitting for the both case specified? Because right now I'm doing...
It was not.
Okay.
It was not. So there is a potential ambiguity where it would then recursively go vertically or horizontally, and I don't care.
Okay, but that's fine, but that's different from...
Yes. So I tell you what my solution does is, I didn't remember. I didn't remember what my solution does, so it doesn't matter. Yes, so I'm not checking in the test cases that I have, once you get the basic splitting right, like for example with the blue one, I don't care which one of them is blue. As long as any of them is blue, I'm fine.
That superimpose statement is meant to be used when we come across like the final square.
That's correct. There's that superimpose thing is for a colored square with a frame. So all you ever need to do is you call that superimpose thing, you just copy and paste it for a small rectangle, and for the larger ones you call HC append or VC append with the split ones. There was an interesting question on Piazza where someone said, well, what about the X and Y coordinates?
We're not doing it relative to anything else.
Yes, so that is the nice thing about using HC append and VC append. They do the heavy lifting of figuring out the X, Y coordinates. You just need to specify the width and the height.
I hadn't realized that they were putting when you do the HC or VC append, it puts it on the inside of whatever you append something and then you append to it again and it puts on the inside.
Yeah, it just sticks them together, right?
Right. Well, sometimes it puts it on the outside and it sticks on the outside. It's not anymore.
No, all HC append does is it takes a shape and another shape and it puts them next to each other. There's no inside or outside. It just takes the bounding of the shape. As it happens, whenever we put two things together with an HC append, they have the same height. And so they will exactly match, except of course for that one poor fellow where it wasn't the case in Piazza.
The Picasso one.
Yeah.
See, that's what I was worried was going to happen. I wasn't wrapping my brain around the recursive nature of calling UCBC.
I use this different random number for the top split,
Yeah.
bottom split, and that's what caused the issue.
Sure. I mean,
I figured it out.
Yeah, there's a million ways, that you can accidentally get it wrong.
I thought it was cool though. So
Totally, yes. Yes.
I think there was some discussion concerning using define versus let rec. When we're like passing the RANDs list like around all of these like stack frames, is there any difference in using either of the two, define or let rec?
I don't
like all within the Mondrian function itself.
I don't think so. I mean, there's basically two strategies that I can see. What I think is the more Lisp-ish strategy is that inside the definition of Mondrian, you have a big let rec, and one of the definitions is Mondrian helper. But
That is the what strategy?
that's, I think, the strategy that like a scheme programmer would employ. That way, the Mondrian helper is nicely hidden in it, and also that way the Mondrian helper can access the width and height parameters of the Mondrian function without having to have them passed along in the helper. So that would be my recommendation. You're going to learn more, I think, from that setup. But it is true that you can have a bunch of top-level defines by making it so that you pass the width and the height to the helper explicitly. That way you could avoid the let rec. You could really define everything on the top level and go from there. I don't think it's as instructive, so I'm not recommending it, but you can certainly do it. The random numbers, they're an explicit parameter no matter what, so it doesn't have anything to do with anything.
Yeah.
Here's what you cannot do. And I need to change the rubric to make sure the grader checks for that. You cannot use set exclamation mark to truncate the random numbers. Because that would be a mutation, and we don't want to have any mutations. So as long as you pass the random numbers explicitly, then you're fine. And it doesn't matter whether you use a let or not.
When we make the cut, do we recurse into either the leftmost or the topmost first? Or
If yours works, I don't think you should change it. And I know that what I first do is I first do the horizontal and then the vertical, but I don't remember in which order I take the random numbers. So I don't think it's that important. Yes?
So, just out of curiosity, I've already written my Mondrian generator that uses the pin over method of.
For generating random numbers?
Yeah.
Oh, I couldn't care less how you generate the random numbers.
No, fuck that. It's the pin over, was it picture minor instead of using VC?
Oh, that I don't know if it works.
No, I used it already. I have.
And it works. If it works beautifully and it produces the same output, I don't care.
Okay, cool.
Yes.
It's just going to be more work for me to like change it at this point.
Okay. I think the HC append and VC append are dead simple, but if you have some other way of combining the pictures, I don't care. Just don't tell anyone on Piazza, it'll just confuse the issue.
When using lambda functions inside the let rec, you're always confined to like the one-liner, is that right?
No.
Can you do anything, like make any side effects?
Well, you cannot make any side effects because that's the rule of this assignment that you can't make any side effects.
Well,
If you needed a side effect, for example, to print a debugging message, you can do that in any lambda. You can say lambda and then your parameters, and then afterwards you can have as many statements as you like.
So it'd just be like essentially making another.
Well, so the only side effect that you can usefully make of the assignment is printing a debug message. There's nothing else you can do, because don't try anything with set exclamation mark or anything. To rip it out later is going to be more work than avoiding it in the first place. But if you wanted to have more than one thing going on, you can put as many expressions as you like in the body of a lambda.
In the body of what?
Of a lambda expression.
Oh, I see, okay.
So
You
you,
can only do that in
no, you can have as many as you like. The value of the lambda is the value of the last expression.
Okay.
Same thing with the let. If you have a let, is whatever many you want. Yes. But it's not in the final thing that you're going to turn in, you're going to take out the print messages, and then there'll only be one. Other questions? All right, let's hope we beat that to death. So the point of today's lecture is to go a little bit more into types. So you've seen generic types on last Wednesday's lecture, and you've seen how you can use them to have rich types, like we had as an example a generic linked list. Here is a list of elements of type E. The head is an element of type E. The tail is a list of the same type. We put a little plus in here to say that's a covariant list. So when you have a list of, here for example, I have a generic list of strings, then I can convert it to a generic list of any's. You use type bounds to do things like defining how cons works. So if you have so we're defining this inside a generic list of E, and now we want to add something in there of type H. Well, this is a typo, by the way. It should be H:H. Then we're getting a generic list of H's out of that. So, for example, if I take a list of string, like what I have here with Fred and GMT, and I stick a 42 in front of that, then it has to find a common supertype that in this case would be any, and that would be the result type. So this is the definition of cons with this exactly defining what those types are. I'm redefining it here with an operator, : just for beauty. It makes it easier to read. I don't think I did that in the last lecture, but today we will. So the : is just a function like cons. If you look at these two lines, there's no difference between it, except I rename cons to : and then I can use it in this operator syntax. There's a bit of a wrinkle about what do we do at the very end. No, when I have the empty list, the empty list is defined the way you see it down here. It's a case object, not a case class, because there's only one empty list. Now, because there's only one, it can't be parameterized. If it was parameterized, there would be more than one. So I have to have it extend a G list of some type, because the empty list is a G list. There's two kinds of G lists, the empty and the non-empty case. And so I need to put in a type in here. And there's this clever type called nothing that you can use in this case, whose properties have been finely tuned to just work. So GEmpty is a G list of nothing. All right. So you've seen in the previous slide how the generic list is clever enough to figure out that the type of the list is the common supertype of all of the elements. But that may be clever, it's just not very convenient. Here I'm making one of those. So LST is a list containing L, sorry, 1. It's a number. And then the string Fred, and then I guess it shouldn't be nil, but GEmpty here. And now I want to uppercase this Fred here, as one does. What do? I say, well, I get to the tail. That way it starts with Fred. I take the head, that is Fred, and then I call to uppercase. But that won't compile. Why not?
It's an any and not a string.
It's an any and not a string, exactly, right? And so that's not so nice. So what I really want is when I write down L and so 1 and Fred, I want a list that's a list of integer followed by a string. Now you might say, why? Couldn't you just use a tuple? Okay, so let's run with that. Can I use a tuple? Sure, I could. A tuple has a type for the first and for the second parameter, and instead of using a list, I could say it's an int, comma, string tuple. Now let's say I want to have two of those things, where I know the type of each of the components, but they're not always the same, and I want to append them. So let's say I have a thing that has an integer and a string, and another thing with an integer and a string. And I want then an int string out of that. So I would like to write an append function. Well, can I do that with tuples? I could if I knew that the first one had length 2 and the second one also had length 2. I could write a generic function that takes a t1, t2 tuple and a t3, t4 tuple and turns them into a t1, t2, t3, t4 tuple by just putting the elements in the right places. But what if the first one has length 3? Then I would have to write a different function. I cannot write in Scala a generic function that takes a tuple of arbitrary length and another tuple of arbitrary length and appends one after the other. Because I can't write t1, t2, and so on. Right? Each tuple type has a definite number of slots. So that's what I want to be able to do with what's called these heterogeneous lists. So it turns out that it's possible in Scala to define a new data type that's not a predefined type in the language, that is a strongly typed heterogeneous list where each of the components of the list can have a different type. So that's what I'm going to show you in the next several slides. So here we're getting going with this. So I'm making an abstract class H list, and that's kind of the same thing as the generic list that you saw before. H is for heterogeneous. And I have a head and a tail function. They're abstract. I'm not defining them. I just have to give their return types. Head returns an H. That's the type of the head. And tail returns a T. That's the type of the tail. So I'm going to say an H list has two type parameters. The head is unconstrained. It could be anything. And the tail, well, the tail of a list is a list. So T must be a subtype of an H list. An H list of what? I have no idea. Some H list, where the head type of that tail is something, and the tail type is also something. So that's how you write it in Scala. So now I know what H list is, and there are two cases, the empty case and the non-empty case. So the empty case is again a case object, H empty, and it extends an H list of nothing, nothing. So that means there's no head type, there's no tail type. I have to define the head and the tail functions. Here's the head function. So the head function calls this thing, this triple question mark. Triple question mark is actually a function in the Scala library. That function throws an exception when you call it. So somewhere in the Scala library, someone said def triple question mark equals throw some exception whose name I forgot. What is the return type of triple question mark? It's a Scala function. Every Scala function has a return type. What is the return type of this function? Unit? It's not unit. It is nothing. So a function can only return nothing if it doesn't return. So because the function throws an exception, it doesn't return, and therefore it's okay to declare it to return nothing. The tail type is also the function that yields nothing, because you can't take the tail of an empty list. Now let's look at the non-empty case. In the non-empty case, we can construct a non-empty list out of the head and tail. And so here, by doing it like that as a case class, I automatically get the head function that returns the head that was passed in, or the head method, I should say, and I get a tail method that returns the tail that was passed in. That's how case classes work, that you get an accessor method for the construction parameters. And those methods override the abstract methods that you've seen here. Now, the other thing that I want to define is how to construct things. So I want to define cons. In the empty case, let's see what cons does. It takes as its argument the tail, and so now I'm making the head. There's a new head, and that new head could be of some type. I don't know what it is, so I parameterize by that type. And I'm now getting back a non-empty list whose head is A, whatever was passed in as the head, and whose tail is empty, and I can just write this. There's only one empty object. And for the non-empty case, it's the same definition. So probably I could have moved that definition up to the abstract level. Okay? Now when I do that, and now I declare a list like this, 42 : Fred : H empty, then I will get a list back, and the type is reported by the Scala interpreter, and it's going to look a little ugly. It's going to say the type of this thing is an H non-empty of int, H non-empty of string, and then H empty dot type. For a syntactical wrinkle, that's how the type of an object looks like. It's the name of the object followed by the word type. And that accurately reflects what we're doing, right? We've constructed, first of all, an H non-empty of string H empty, and then stuck another H non-empty before that because the cons goes from right to left. Now that's an ugly looking type. I can make it appear a little bit prettier with a bit of Scala type magic. I can define with the keyword type new types. First of all, with the easier ones, I say H nil. The type H nil is the same thing as H empty dot type. That way, whenever Scala sees H empty dot type, then it's going to instead use this H nil and show it as that. And then I say the type : Interestingly enough, in Scala you can call a type : It's a type constructor. That means it takes type parameters, and a : takes two parameters, H and T, and then it actually is a synonym for the H non-empty. And here we're specifying a bound on T that it has to be a listing. So with those two, then the type of result can be written as saying result is an int followed by a string followed by nil. And that's kind of nice, right? Now I can declare these types in a very pleasant kind of way. This is all a type that I have invented. This was not a built-in type in Scala, but now it looks like a built-in type, right? And it looks like syntax that the Scala people could have come up with. And so it's nice that you have this flexibility in Scala. All right, so now I've succeeded in defining a type for heterogeneous lists. Now let's move on to the append, which was the reason that I wanted to do this in the first place. So I need to add an append method to the HList class. So what is append? It's a method of the class. That means it combines the receiver, an object of that class, with a second list that I call here LST. And I have to say LST is of some type. I call that type L. And what do I know about L? I don't know what L is, but I know it's a subtype of a list of something. Now that's the definition of append with the parameter object, the type of that object, and then the type parameter. It's an abstract method, so I also need to provide its return type. So what should we put for the return type? Now you could say, maybe we can put in what it is. It's a list. So maybe it's just an H list of something, comma, something. But it turns out that's not enough. And so there is a trick that we can do to make it work. I'm going to say that the return type of the append method that you see here, the return type of the append method is the type append with an uppercase A. And it depends on the type of the thing that I'm appending of it. That's L. So append of L is some type. And over here, I'm going to say, okay, this is the type of append, and I'm going to say in the abstract case, I don't quite know what it is, but it's a subtype of H-list. So an append is an H-list. Now we're going to be going into some Scala that we've never covered, so I'm just telling you that you can do this. Now what you can do is you can refine this abstract type in the two subclasses. So we have, again, the empty and the non-empty case. And in each case, I'm going to say what append is. Let's look at the empty case first because it's simple. When I write the function, the one or the method, with a lowercase letter, then I have to decide what does it mean to take an empty list and append an arbitrary list. Well, then I get the arbitrary list back, right? Empty list followed by LST is LST. So now I need to say, what is the type of this? Well, the type in general is append L. So now I'm going to define what append L actually is in this case. And it is L. It is whatever this list type is. So if I have an empty, then the type of append is the type of the list that's being appended. Now what about the non-empty case? Let's first write the function or the method. Here is append. And so I make a non-empty list using the head of my current list, and then I recursively append my target list LST to the tail. And I cons those two together, and that recursively gives me the append. Now I need to come up with a type of this. Well, let's see, what do I know? I know it's an H non-empty. That's a type. So here I can say, okay, it's an H non-empty. I know the type of the first, because that's head. Let's see what head is. Well, it's the head of this list. It's a list where the head type is H. Sorry, here. And so that's this H here. Now what is the type of this thing here? So I know what the type of tail is. It's T. I don't really know what that type is, but I know it's a subtype of H-list. And therefore I know it has a nested type called append. And so I take the type of tail, which is T, and I say inside there is a type append. And that is the return type of this thing. And so by encoding the sequence of method calls into the types, we give Scala enough information that it can now figure out what is the type of doing this. So here I'm taking a list LST, and it has type int : string : H empty. And now I'm taking the list and I'm appending it with itself. And that gives enough information to Scala to say, oh, this is an int string. And that's kind of amazing. So as the implementer of append, then clearly you have to suffer, right? This is not fun to have to figure out what these obscure types are. But the user of append doesn't care. You know, if I just consume this library and someone else has written it, what do I care if they had to suffer? And you get a perfectly natural type. You get a list where each of the component types can vary, and where the list remembers what those are. You throw them together in some way, and it still remembers.
Is this really that useful? Because each one of these is like an own distinct type, right? Like if I were to pass this to a function, like wouldn't I just pass instead an int to string and int to a string?
So it is true that if you pass this to a function, the author of this function has to suffer. Right? Because all the author of the function can do is declare this as an H list. If you want to pass an arbitrary thing as an H list of something comma something, and then it's hard to deal with. And so it only becomes useful in a situation where you have a predefined set of functions, such as append and reverse and whatever else you may want to do it, that someone else already implemented. So it's I understand what you're saying is that it's in general not if you want to write a function that says I want it to work on arbitrary H lists, you're in it for a lot of trouble.
I'm saying
but that's not what's intended to use. You would use it to say, here's a function that takes something that has an int and a string and an int, and maybe then you get another string from somewhere else, and it returns the thing with all four.
But this is something like struct int string int, and I can pass like just a single struct of that to a function.
Yes.
But I could also just pass separate int string and int. So I don't see how this is like.
I mean, it does not solve world hunger, right? But if you, for example, have a map and you want some of these map entries like that, you can.
So I guess it's kind of a way to define like a tuple.
It is just like yes. Just think of it as being tuples. And when you use tuples, you did not complain about the fact that you couldn't append to generic tuples. You use tuples because they were kind of handy things. So this is exactly like tuples, except that someone out there is able to append them. And do any other listy things with it, like reorder them or in some way reverse them or whatever. You cannot write today a generic function that returns it that reverses a tuple. You have to do it in an ad hoc way. So it is basically tuples on steroids. Maybe not a lot of steroids, but tuples with aspirin, vitamin C. But what's and we've never needed to use them. So, in fact, they're not a part of the Scala standard library. You can get add-on libraries that provide this feature. The point that I wanted to make is this is kind of the simplest example in Scala where you can express a set of types and operations on instances of those types that you could not do in a more traditional language. Like in Java, there's no way you could do this. The type system that you have in Java with the Java generics does not let you express these these nested types. So there's no way in Java to build a type-safe heterogeneous list, or tuples, for that matter. So Java has no tuples, and there's no way for you to provide arbitrary tuples. Whereas in Scala, if Scala didn't have tuples, we could write them. Yes?
When would you use a heterogeneous list?
Well, when would you use a tuple? You can use a heterogeneous list every time that you otherwise used a tuple, but you can then also combine them. Right? There's no way for you to append two tuples, other than doing it laboriously by hand.
So
There's no way to swap elements in a tuple or something, other than again laboriously doing it by hand. And with an H list, one can provide any of the 100 or so standard functions could be applied to an H list. There's a dumb thing. You have like a tuple. You have an H list, and then you have an H list of corresponding functions. You could map them or something.
So this is like, so if you want like a tuple of 3 ints, and you already have a tuple of 2 ints, you can do like tuple of 2 append a single int. Instead of having to write tuple of 3 ints, I guess you reuse.
You could save your life moderately in some instances that have to do with operations like appending or zipping them, like interleaving, for example. That kind of structural operations you can program once and for all with heterogeneous lists, and you could not do it once and for all with tuples. So I don't want to oversell heterogeneous lists, but I do want to strongly push this feature that you can create new types, brand new types with complex behavior out of nothing so that they're checked at compile time. So that is the key observation, what you can do with these languages. And so people will ask me, now why should I learn Scala instead of Kotlin? Kotlin is a nicer version of Java, has a nicer Scala-like syntax in many ways. And if all you want to do is get a little bit nicer syntax, then Kotlin is great. But Kotlin does not allow you to do this kind of type magic, so you're not going to learn what the next generation of programming languages will be like. There is a great desire by people to give more and richer types in all sorts of things. For example, when you, as a realistic thing, when you write an object relational mapper, it is really nice to be able to say this is the exact type of a table in the database. And that you say, I know this is students, and students, the first column is string, the second column is string, the third column is double, the fourth column is int. And that's something that you can encode with a type system that can do these kinds of encodings. So the Scala OR mappers, they do that. And they do this type magic so that you can write completely type-safe queries. So that when you write the query, there's never an issue of whether later when you run it, whether it might fail because of a type error. Yes?
How is that hashtag different from like that type down? Because you were saying it.
Well, I really don't unfortunately have the time to get into it. It would take us several hours of type theory to get that. This is what's called a dependent type. So this is the append type that lives inside this T. It's different from all other append types. And so this T itself is most likely an append. So in the end, you're going to get some crazy type that's an append of an append of an append that comes down from the recursive definitions. Now this is a compile time recursion only, right? At runtime, it doesn't do you any good. But when you have a thing like this, where this is appended to itself, the type at compile time is computed by appending these types at compile time. Okay, I'll give another example of where this is kind of useful. And I need to do a little bit of introduction for that. So there is let's say that I wanted to convert certain objects to JSON. You know what's JSON? It has numbers, it has strings, it has arrays of numbers and strings, and arrays for that matter, and it has objects that are like maps with key value pairs. And so I will say that how do I convert an object? Well, presumably I have some converters for different types. Like I can define a JSON converter of type int that turns an integer into a string containing, or into just the integer. Integers go to themselves. I can convert a string by that. I'm doing that here by taking a string. How do you convert a string to JSON? You put a double quote in the front, you put a double quote in the back, and then you escape the backslashes and the double quotes that you have in the middle. And I can do the same thing for lists and so on. So here's how you would package that in Scala. Kind of like in Java, you would come up with an interface for the converter. It's a typed interface, and it has a function convert that takes an element of that type T and converts it to a JSON string. Now, of course, then I can very simply write a generic function to JSON that takes an object of some arbitrary type T and a converter of that same T, and then it calls on the converter to convert this object. But so far, nothing exciting is happening. Here's the first thing that's nicer in Scala than it is in other languages. I can make it so that the converter is automatically located. The way to do that is to define the converter parameter as what's called an implicit parameter. You see that down here, where this to JSON method has been rewritten so that there's a closing parenthesis and then a no opening parenthesis is curried, and then the converter is now declared with the magic keyword implicit. At this point, I call just to JSON of Fred. I don't have to specify a converter, and the implicit tells the Scala compiler to look around for an object of type JSON converter of string, because this thing is a string, that is in what's called implicit scope. There are various ways on how you can bring such an object into implicit scope. Here's an easy one. I can declare it as an implicit object. So this is kind of you would put this somewhere, you would import it from somewhere, and then this converter has been brought into scope. So when the compiler sees to JSON of Fred, it's going to say, well, I need one of these implicit conversion objects. Then it would look around in various places, it would find this one, and it would take that, you don't have to name it. So it's kind of a global that's picked, but it magically the right one is picked dependent on the type. So by putting a number of different converter objects like that into scope, then you can control what happens. Yes?
So let's say you don't include one for string, like how will it still compile?
No. So now let's say that you didn't put in any for string, or you put in 2, then it will not compile.
But then, like, how does it know that you need to use string?
Well, because it looks at the type of the first parameter.
Oh, so it looks at your call.
Yes.
And then make sure for all the calls that there's a implicit object.
Yes.
Okay.
Yes. So each time that it calls it, then it says, okay, now I need to complete that second curried parameter here, and that's when it starts the search.
Okay.
And so that's kind of a syntactical convenience. So if I call JSON, or to JSON, of new file Fred, where this is it's a file object, then it's going to try to find a thing that is a JSON converter of java.io.file. If it doesn't find one, then it complains. You could, of course, at some point define one if you have a way that you want files to be converted for JSON. Okay. Now, there's actually another way of putting that, and that's maybe slightly prettier. So when you define the toJSON function, you can, instead of using this implicit syntax here, there's an alternate syntax that people prefer these days. You say that I'm going to put a type bound on T, and the bound looks like that. It's a colon JSON converter, and that means that there needs to be an implicit parameter of type JSON converter for this type around somewhere. And then we just pass the T explicitly, and there's no implicit behind it. Now, how do we retrieve the converter? There's a nifty function called implicitly that will find the one and only object that matches this type if it exists, and otherwise give a compile time error. And then you can call convert. So that's not super important, it's just a different way of writing the same function. I brought it up because you have seen elsewhere, like I think on last Wednesday, I said, there's this unsatisfactory thing with the less than percent and the whatever that comparable equivalent was, the ordered, that's what it was called, was ordered. And so the modern way is that there's a thing called ordering, and it uses the same implicit mechanism. But whatever, that's just aside. So now I have this implicit object, and so there is, I want to do the same thing for lists. So I want to have a list JSON converter that converts any list of types that are themselves JSON convertible. And there is a syntactical nonsense that I have to go through to deal with the fact that I can't make it as an implicit object. So notice here I have an implicit object. And objects can have type parameters. The syntactical wrinkle is I make an implicit def. So don't worry about that. That's just some Scala minutia. So, and otherwise it's the same thing. And like I said, never mind the def. It converts lists of type E that themselves must be convertible. It produces a JSON converter of these lists. And here I'm making it. So it's a new JSON converter of list of E, and it itself has a convert function. And what does the convert function do? Is it takes each of the elements of this list, calls to JSON on it. That will succeed because each of them is convertible, and then it makes a string by putting a bracket in the front, a bracket in the end, and a comma in the middle. The point of this is I can express the fact that a list JSON converter exists for a type E, provided that all of the elements themselves are convertible. Now I can call to JSON of list Fred Wilmer, and that'll work because Fred is a string, and strings are convertible. I've defined an implicit object for that. I can call to JSON of a list of a list, because these integers 1 and 7, they're convertible. Somewhere I have an int JSON converter, and therefore this list of int is convertible, and now I have two of these lists of ints in there, and therefore a list of the lists of the ints is convertible. But if I put into the list something that's not convertible, like two file objects, then it does not work. Then the compiler will say, I cannot compile this. Now again, this is something that would be difficult to do in Java. So here we're using the type system to say that a list is convertible if and only if its element types are convertible. And at compile time, this feature is checked. Now think of how you would do this in Java. In Java, you have a phenomenon of serialization, where you say a list is serializable when it's, well, first of all, you can have objects serializable. What do? You use inheritance. You say if they implement the serializable interface. What about array list? Is array list serializable? Yeah. So now let's say you make an array list of a bunch of things that are not serializable. What happens when you try to serialize it?
I think you get an error, right?
Runtime or compile time?
Runtime.
Yes, you get a runtime exception that says, here there's a watermelon in there, and watermelon does not implement serializable. In Scala, you would get a compile time exception, right? So at Scala, it can track these things at compile time. So that is the power of a type system, that an advanced type system can compute certain properties at compile time and then take advantage of them. And so that's, like I said, that's the future of types, that it'll become more and more possible for us to encode whatever properties we want in types, so that fewer things have to be checked at runtime. So think again of the example that is said with elements in a database. Right now, when you use JDBC, everything is a runtime type error, right? You give some queries, and those queries may or may not succeed at runtime because you're trying to put in a string where an integer is expected. And a Scala OR mapper can be written, and they have been written, more than one, that uses compile time type checking for these things. So that's a great advantage, and that's really what is interesting about Scala. The unhappy thing is that it's really hard to do. So I have a lab here that we're not really going to have time to do that, so I'll just walk you through the answer of one of them that says, well, we've done this thing with append for these heterogeneous lists. Let's do it for reverse. And so what do we have to do? We have to define what is the type of reverse in the empty and the non-empty case. And in the non-empty case, of course, I also have to implement it. Well, in both cases, I have to implement it. So let's implement reverse in the empty case. What's the reverse of an empty list?
It's empty.
Yeah. So how do I write empty? I can just write this because it's the empty list. Right? I'm reversing the empty list. So over here, I'm going to reverse a non-empty list. Okay, how do I reverse a non-empty list? So I think I have to reverse the empty list. No, sorry, the tail. So what is this? Tail dot reverse.
And then append the head.
And then append the head, but I have to make the list of the head. And how do I do an empty list? H-empty. Empty. Like this. Okay. What's the type of this thing?
Should be the same time. Oh, no, wait, no.
No, it can't. Yeah. So you think if you have a homogeneous list, then sure, it's the same type, right?
Yeah.
But in a heterogeneous list, all the types need to get reversed.
Wow.
So I need to figure out how to write such a type. So here's how I do it. I figure out now what is the type of of tail. It is T, yes. So whatever the type is, it's something that sits inside T. And because I'm reversing, it is one of those reverse types. Now, reverse takes a type parameter. Or does it? No, it doesn't. Yes, that's a type like that. But I'm not done, right? I'm also appending. So I also need to encode the append into the type information. So the reverse thing gives me some type of the reversed thinger, whatever it may be. And now I have to encode the append type of that. And now append takes a type, namely the thing that's being appended to. Well, what's being appended to? It is an H non-empty. And that has the head in here. What's the type of the head? H. And then the other type is H empty. Okay, that's what you do. So, see if we have the courage to send this off. Okay, so if this autograder is somehow very slow with Scala, so we'll see whether it works or not. But the point of this is that, like I said, it's unpleasant to do these implementations because you have to do this type encoding. Because it's h-empty dot type. So it's unpleasant to have to do this encoding, but that's Scala. That's because they have not figured out how to automate that part. The next language may well automate that part, and so we may be finding that this type level programming becomes easier. All right, that's what I got. Any final questions? Oh, if the question is this going to be on the exam? No. This really is only to show you the outer limits of where we are with this technology today, and so that you get a glimpse for that. Now, some of this will at some point be harnessed and be a part of the future.
Well, no, I just
All right.
Still submitted.
The more
Yes,
errors
sir.
aren't too common, the better.
Sorry, you thinking about the project last class?
Yeah. You haven't worked yet?
Oh, yeah.
I don't really know. I looked at it, but I don't know if it should be closest to the
the game.
You guys got it.